Welcome to Blue 2, which can be summarised as if you want less bugs in your code, then don't put as many in. But first, please subscribe to the channel, click on the like button, click the bell icon to get notified, and support me on Patreon if you can. There's a link in the description below. Now, the first part of this presentation is as much about philosophy as it is about code. Tried to keep the code to the minimum, and most of it comes towards the end. But basically, defensive programming is the way to prevent getting bugs in your code to start with. Because the less they have in there, the less it takes to get them out. So here's the thing. Years ago, I had a young lad I was training up. He asked me a question, I reeled off an answer. Came back an hour later and asked me another one, reeled off. And after about 3 or 4 of these, he said to me, "Oh, wow, how come you know so much?" And my answer was, because I've made a million mistakes and I've done everything wrong that it's possible to do wrong. And I'm not actually that smart. I've just got a good memory. So what follows is the distillation of 46, oh, that pains me to say that, years experience, and some golden rules, techniques and habits that I've slowly developed to try and keep that number of mistakes at only 1 million. There's an old saying that says an ounce of prevention is worth a pound of cure. And the term defensive programming, even if you've not heard it before, it's been around quite a long time. Probably not quite as long as me, actually, but here's my interpretation of it. As I said, the less bugs you put in the first place, the less head scratching and swearing you have to do to get them out. Because bugs don't just get in there, you write them. So this isn't going to be a list of low-level coding practices like, always put a 3 after an alloc, which is kind of dumb. But a much higher level philosophy, starting with all code fails, so design for failure. Now, it might sound trite and facetious to say that we generally design and write our code as if it were going to work. Why wouldn't you? But the italics, the as if, it's deliberate. And let's just stop and think what we're saying here. If we accept that all code has bugs and that it's kind of impossible to write without it, then why do we behave as if our code doesn't have bugs in it? We know at some point it will fail, but rarely do we adapt our style to design that in from the first blank screen and tippity-tappity on the keyboard. We write code as if it's going to work, and that's not how it works. So the first golden rule there is design for failure. So let's look at a day in the life of the happy programmer off to work. Comes out of his lovely house, jumped into his lovely car, drives to the office and sits down to work. Now the house he's come out of has got locks, smoke alarm probably, and an insurance policy. The car he jumps into has got locks, seat belts, airbags, impact bars, all sorts of gizmos and gadgets for safety and protection that have gradually been improving over the years as more is learnt about how cars fail when they crash and what damage they can do. And things are designed in and built in from the start to prevent or minimise those things happening. And on the way to work, he probably goes through a few sets of traffic lights, which are again have a single sole purpose: to prevent problems which are known and expected to happen. Gets to the office, which has got CCTV and security guards. Can you see where this is going? Because he then sits down at his desk and writes code that doesn't have all of that stuff built into it from the ground up, generally. Now, obviously, good programmers know how to use try, catch blocks, result and error code returns and asserts, but ask yourself this. What percentage of those are bolted on when there is a bug versus those that are written first as a kind of framework into which you drop the actual code that you're being paid to write? Or doing for free, as I do, but there you go. Because just asking that question assumes that there is a case when there isn't a bug. And if you're designing for failure, there's always a bug. So the code should always be there. Now the asterisk is there to remind me that I'm talking mostly about the development cycle. As your code improves, you can afford less diagnostics in it. And as it finally moves towards production, you then want to have none in it for efficiency and speed. Now, the best solution, in my view, is to have diagnostic code built in from the ground up, which is configurable, so you can set levels and it can splurge out more and more and more as the levels go, and less and less and less. And so you can fine-tune it as it improves and then turn it off altogether to put it into production. And we'll look at how I do that in a little while when we get to the codey bit. So another question for you. Do you design top down or bottom up? Most of us are probably familiar with this kind of diagram. And generally, when we're thinking about the business logic of what our code is actually going to do, that's pretty much the way everybody does it. And then setup might have one or two sub modules. Loops probably got dozens. Close down might not have many. But let me ask you that same question again about one of those. Because you don't put a whacking great box up and think, oh, I'll have a door in the middle and then knock a hole in the wall, do you? And also you think, oh, well, I'd like some wiring here and some plumbing here. Well, it's too late because the concrete base is laid. You know, you have to build a house from the ground up. You have to design it carefully, dig the foundations, wait till they dry, make sure they're solid, then put the next layer on. And that's the way that diagnostics should be approached and built in to your code. So in my defensive style, first come the diagnostics, and they are built ground up. Once you've got a decent framework which will help debug itself, then you can start putting the top-down application logic on it. So this diagram is taken from a kind of classic description of how operating system kernels operate in a series of what are called privileged, or some people say trusted, rings. So the most trusted or privileged code is at ring 0, the lowest level. And that, in our diagnostic scenario, that is where you've got to have bomb-proof code. You have got to batter that code to death so that it cannot fail. And once you've got that, you can then put a next layer on which calls those bomb-proof routines, and therefore you trust what it's telling you, because the worst thing you can get that causes a lot of harm is diagnostic code that lies to you. That really does slow you down. So you've got to get your diagnostics right. So we build up this level of trust, and by the time we've got to ring 3, we're fairly happy that if ring 3 tells us X, Y, Z has happened, it's happened. So here's our first golden rule, our first, next, whatever, another golden rule. Start by writing the diagnostics. I've got a hex dump routine in one of my firmware products that we'll talk a little bit more about in a minute. Basically, it takes a memory address pointer and a length, and it dumps out to the serial monitor the contents of that memory in hex bytes. And when I first wrote it, I thought, well, it'd be nice, we'll put a parameter in there so your user can determine the width. And then I thought, no, hold on a minute. Somebody at some point is going to put some stupid value in there and that's going to bust. That somebody, probably me, fat-fingered typing, however it happens, doesn't matter. And I thought, no, bugger it, that's coming out. It's going to be 16 bytes wide and that's the end of that. And I'm going to hard code it in there, something I don't normally do. But that routine now is absolutely bomb-proof. You give it any address. It's not totally bomb. See, here I go already. It's not totally bomb-proof because if you give it a length that takes so long that it causes the watchdog timer to time out. Anyway, the point is, I know what it does and I trust it. If that thing tells me that black is white, then I will believe it. So at ring 1, I might have some function that moves one buffer to another buffer, and I can have a ring 1 diagnostic that says call dump hex on the input and the dump hex on the output. So because I trust the dump hex so much, I kind of automatically now trust my ring 1 diagnostic that says, well, the output buffer and the input buffer are the same. If it tells me that, I think, well, I believe it. Must be something else wrong. And this helps you narrow down the range of possibilities and hone in on the bugs much more quickly. So let's start looking a little bit codey. And let's look at some kind of typical things. Now, in production code, you might have a function 1 that's just a single line and does that. Now, obviously, the examples are ridiculously trivial, but this presentation isn't about code quality or style. It's about principle and philosophy. So there is what some people would call the easy way. I call that the hard way. And the reason it's the hard way is because if it does go wrong, it does nothing whatsoever to tell you what went wrong or give you any clues about why. So you're immediately into a bug hunt. So while this second method may be longer and take more time to write, it's actually easier. So whereas in the first one we have a line of code count with logic 1, diags 0, in this second version we've got logic 2, diags 2. We've got twice as much diagnostic code in there as we've got actual code. And this is what I do on all of my functions as I write them. Before I write them, I've got a kind of templated insert and it goes whack and sticks in a diagnostic line which shows the value of all the parameters on input, and then I never return the actual value. I always have a variable of the appropriate type to hold the value, and then just before I return it, I show what I return. Now that is just a technique that you have to get into, because if you think back to number 1, you think, oh, I've got a problem in somewhere. Well, it can't be that function 1. That's only one line. And you get that kind of blinkered thing where you can't see the wood for the trees because you wrote it, you know what it expects to do, so you think that it does it, so you say, well, it can't be that then. Well, you don't get the choice in the second version. It tells you that 2 and 2 came in and 4 came out. So if you're getting 5 out of it, then you think, well, it can't be that function. It's got to be something else. Might be that the function that calls it has corrupted the stack and just happens to point to a thing that's got a value of 5 in it. But if you didn't have this, you could spend hours looking at this, which is the wrong place to be looking. So the even easier way is I don't use printf like that. I normally have a macro which has a templated function call in it, so that I just get a single line at the beginning and a diag print 0. I have levels. Here's my kind of trust levels. It's either a trust level or it's the amount of information it splurges out. We'll see that again in a minute. But so I've got a nice balance. I've got 2 lines of logic, 2 lines of diags, and I get told what's happening. Now, because of that macro, I can turn off whether I get told what's happening or not. But that goes in before I even think about what that tiny one line in the middle is going to be doing, which is the actual code. Thinking about classes, something similar happens. Debug in the constructor, showing all the input creation values. Debug in the destructor to tell you when it goes out of scope. There's our little internal function, and before even looking at that, look, always I put a dump function in there, and the dump function just splurges out everything it knows about the instance of that class. So obviously our dump function, our function follows the rules, as does the dump function. Yes, I'm trusted, but hey, I just got called to run. And it, simple example, just prints out the values, of course. But on a slightly more advanced scale, I will, in many instances, do this. Again, putting all of this in before any actual code. I will have a static vector of class pointers, and then I will have a static function which iterates the vector and calls dump on every one of them. In the constructor, it just shoves its this pointer into that vector. So at any point I can call simple dump, and it will just dump every single instance of it that's been created with all of its internal values. And you'll be surprised at how many times you think, how did that get there? I've only created 3, there's 4 in there. And that's your problem. It's the 4th one that's in there, that's been in there forever, not the one that you just put in that caused the problem. Without this kind of stuff built in, that kind of bug can take days to find. So if a bug can take days to find, and this only takes you an extra 15 minutes per function, do the maths. So here's another concept I like. I call it code as a tool. Having written that simple thing, I will then go away from the code that I'm meant to be writing, and I'll write a quick and dirty throwaway program, put some scaffolding around it, and beat the living daylights out of it, so that I've got a good idea when I put it into its proper environment that all of the silly, stupid errors that I generally make a lot of I've already sorted out. So every single type of input and output, of course, testing each function, making sure the dump function, this is the way of shoving my dump function back into ring 0, and by exercising it here out of its own environment to know that it does, because I've got simple values in there and I can see those same simple values, I now trust my simple dump function. Right, here is a real world example from my firmware known as Pangolin, which is an MQTT client for ESP. Well, you can see it up there. This is the here's my conditional compilation debugs. Now these work the opposite way round from the rig system, but you know, it's whatever, we live in the real world. These splurge out more information the higher the Pango print number is. So I've got my templated string function. Quite often if I'm doing things with times, I'll modify one of these, and I'll always put the millis value in that string as well, so you can see exactly the time between messages if you're getting timing errors. And then if Pango goes down, so 4 splurges pretty much everything, and you soon rapidly tire of the amount of junk that turns out. Because with Pangolin, which is an MQTT client, 1 prints out the MQTT packets in and out. So you see a TX and an RX. 2 prints the contents of the packet. Well, not the contents of it, it prints the name and the type of the packet. 3. 4 prints not only all of that, but it uses that hex dump to print the entire contents of the package, and it prints pretty much every entry and exit of every function that gets called. So if I put a Pango debug at level 4, I get about 50 miles of diogs to run through but there's so much information there that I am going to find the error quicker than you are. And if you take it down to 0, it compiles it out, so you've got no performance penalty or overhead, and you can just leave that in for production. And this is taken from the current GitHub copy of it. So I leave all that code in. It's not hurting anybody because I default the Pango debug to 0 when I deliver it. Now here's my favourite example, because this really is taking it to the extreme. For some people, for me, it's the way it just has to be done. So if this were in typical production mode, that's a one-line function. It says if there is a callback message, then call it. Let me just highlight that a bit better. If there is a callback message, call it, passing it all of the constituent parts of that incoming structure. That's one line. But if the debug is on, all this extra stuff gets in. So you look at the slot count there. Logic is 2 lines. There's 24 lines of diagnostics in there. And it dumps the entire contents of everything that you want to know about that, what's going on. And I say plus there because in order to activate that, that's done in response to an incoming MQTT message given a particular topic. And elsewhere in the code, if the debugs are on, I subscribe to a debug topic, which is a reserved word in my rules. And this is the thing. So this is the mem portion of it. There's the info portion of it. And looky here, there's the dump portion of it. So if I send an MQTT message saying Pango dump, oh man, do I get a lot of info out of it. So here's the thing. You get the code to do the work. You've got a computer, for goodness sake. Get it to do the hard stuff, not you. Get it to tell you what's wrong with itself. Work smarter, not harder. Code defensively. So we've got a lot of little silver stars within the bigger golden rule. Don't be afraid to write significantly more. Excuse me. Sorry about that. I thought I'd paused it. Don't be afraid to write quick and dirty programs just to test one small untrusted function, because once you've tested it, it becomes more trusted, and the less you have to do it. And don't be afraid to write big quick and dirty programs. I've written programs that are half to 2/3 the size of the thing that I'm being paid for, just to test the thing that I'm being paid for as I build it. And above all, don't be afraid to treat that all as throwaway. You're not throwing work away, because that has saved you work, and it's given you more tools to your toolbox for next time. So golden rule number whatever it is, that the real code, your deliverable, is only part of the end product. All of the structure and the scaffolding and the diagnostics that you sit it within are also part of it. And if you have to throw half of them away, so be it. It doesn't mean you can do without them from the beginning. If you do without them at the end, oh, but that's so much extra work and time, Phil. It isn't, and here's why. Because gradually it steers you into a way of thinking and coding that will save you time in the long run. You build that toolbox of techniques that you can just drop in on day one of your next project, and you become much more productive, much more rapidly. So let's just manufacture a silly example just to prove the point. So imagine that it takes 10% extra to put all that guff in, and you're on a 10-day project nominally. So you, the defensive programmer, you're going to take 11 days, 10% longer than somebody that doesn't put all the diagnostics in. But you're going to cut your bugs out, your potential bugs out, as you go. So Mr. Normal, day 9, while he's kind of streaking ahead, you know, he's the hare and you're the tortoise, he hits a bug. So he hasn't got any diagnostics in there like you. He hasn't got all that 24 lines of glorious splurge. So he spends a lot of time looking in the wrong place, not being able to see what's going on. And after a day, he thinks, oh my goodness me, I'm going to have to put some diagnostics in. What's that, I hear you say? You're going to put diagnostics in? Well, why didn't you put them in to start with then? Because all the stuff that you put in, he's got to now backfit that, which is harder to do, let me tell you. And that's going to take him time. Give it a day to prove the point. Once he's done all that, he's then got to use them and test it. And until that eureka moment comes, you'll find that if you add them all up, he's actually taken 11.5 days and you win. Because an ounce of prevention is worth a pound of cure, and you get the very impressive programmer rosette. So the summary then of my homespun wisdom of 46 years of experience. Expect failure and design accordingly. Start with the diagnostics. Build upwards from trusted to untrusted. And treat the final app as only part of the product. Thank you very much for watching, as always.